All right, what's up everyone? Welcome back to the last chapter of this course, Spacecraft Formation Flying. And as I said many times already, this is by far my favorite chapter because this is closely related to what we do in the lab in terms of research activities in the area of spacecraft formation flying, okay? So, chapter 5, the last but not the least chapter of this course, Spacecraft Formation Flying, SFF. For short. So if you look at the section 5.1 in the lecture note, which is titled Relative Orbit Geometry, there are no equations. This is just a very simple blurb about the historical perspective of formation flying and about the fact that in its most simplest form, formation flying would consist of two spacecraft along the same circular orbit, like that. Spacecraft 1, spacecraft 2, such that the distance or the angular separation between both spacecraft would remain constant as both spacecraft evolve along the same orbit, okay? So the radial separation or the separation between both spacecraft will always be the same because they're both traveling at the same speed. Now, another situation that can take place is if you look at the elliptical orbit case, we have M1, spacecraft 1 here, spacecraft 2 there. Then obviously, because they're riding along the same orbit, but this time the orbit happens to be elliptical, then the separation distance between S1 and S2 will vary as time goes by and will then follow some sort of a sine wave pattern. If you denote rho as the relative position between S1 and S2, it would be bounded yet would oscillate over and over because spacecraft 2 is ahead of spacecraft 1 and therefore would experience a decrease in velocity here near the apogee ahead of time than spacecraft 1. So then here the separation would decrease a little bit and then increase and further increase at the perigee of the orbit because spacecraft 2 would experience the greatest amount of acceleration at the apogee and spacecraft 1 would still be lagging behind a little bit. But overall, the motion would remain bounded like that. Okay, whereas here, the relative motion, which is the motion of one spacecraft with respect to the other, would remain constant in terms of separation distance. So those are the two most fundamental spacecraft formation flying scenarios we can think of, but in practice, this is not how things typically happen because we're going to look at relative motion from an arbitrary direction. So you could have one spacecraft orbiting along its orbit and then another spacecraft following or tracking that target spacecraft closely, yet along a different orbit, which could be on a different orbital plane, such that the relative motion would happen in X, Y, Z of the ECI reference frame, and would not be one of these two very simplistic situations, okay? So all this to say that now that this discussion is kind of over about the simplistic architecture of formation flying, both spacecraft following along the same orbit, that's kind of boring. We're going to have a look at a much more generic scenario where the relative motion happens in an arbitrary direction, okay? And what we're going to do first is to derive the nonlinear equations of relative motion. So in other words, how to examine the motion of one spacecraft from the point of view of, say, the other spacecraft, which it is following, okay? So we're not concerned here about rederiving the two-body equation of motion, which would be the spacecraft motion with respect to the planet. That's no longer of interest here. What we really want is to obtain the motion of one spacecraft with respect to another one, okay? So this is referred to as relative motion. And the first thing we'll do is to derive the exact nonlinear equations of motion for that scenario. And then we will look at simplifying assumptions to then obtain a linear motion or a linear model that will be used to predict the relative motion on orbit between two spacecraft. And using that linearized version of the exact nonlinear motion, we're going to look at how can we carefully select the initial conditions of one spacecraft with respect to another one to obtain whatever type of relative orbit that we'd be interested into obtaining. But all of this will come later on. So first thing first here, let's derive the nonlinear equations of relative motion. Relative, again, in the sense that this is spacecraft 1 with respect to spacecraft 2 or vice versa. To do this work, we'll need to define a new reference frame. Yes, we like those reference frames quite a bit. And this one is going to be called the local, vertical, local, horizontal reference frame, or LVLH as an abbreviation. So if you remember the orbital reference frame that we saw in the orbital perturbation chapter, chapter 3, a couple of lectures ago, you will have an easy time understanding what LVLH is, because this is exactly the same as the orbital reference frame. The only difference being that the origin of LVLH sits on the target spacecraft. Okay, so in the follow-up discussions in this chapter, we'll always refer to a target spacecraft and a chaser spacecraft. Okay, so we'll assume eventually that the target spacecraft is passively orbiting along its orbit, doing its thing, no propulsive maneuvers, and that the chaser spacecraft would use feedback control systems to actively maintain its relative position with respect to the target spacecraft to be whatever it needs to be, okay? But in order, again, to derive the nonlinear equations of relative motion, we'll need this new reference frame, LVLH, which is going to be organized as follows. Is there a figure for that? Yes, there is. Okay. So we have M1. Okay, so this is the Earth. And let's say we have a target spacecraft passively orbiting along its circular or elliptical orbit, it doesn't matter. And then let's say we have a chaser spacecraft on a different orbit, like that. Chaser spacecraft. So let's define a couple of things here. First up, we're going to define the position vector of the target spacecraft with respect to the origin of the Earth as being RT vector, like this. Okay? And that's all we need to define the LVLH reference frame. Because LVLH has its origin directly at the target spacecraft, so LVLH in green has its origin right there, has its x unit vector in the direction of the position vector of the target spacecraft with respect to the Earth. So that would be its LX unit vector direction, like that. It has its LZ unit vector, which is parallel to the orbit angular momentum vector related to the target spacecraft orbit. So I'm going to draw LH or LZ being out of the board towards you, because the spacecraft is traveling like this. Position, velocity, cross product gives you a specific orbital angular momentum vector for the target spacecraft out of the board. Right-hand rule, nothing new here. And then, as per usual, the LY unit direction will be obtained by the cross product of LZ with LX, and would be something like this. Now, along a perfectly circular orbit, so in other words, if you assume that the target is following a circular orbit, then LX and LY would be perpendicular at all time, but that's only valid for a purely circular orbit, which may not be the most generic case, okay? So again, LVLH, origin at target spacecraft, has its LX unit vector aligned exactly like our T vector, but then because LX unit vector is a unit vector, we need to divide that with RT magnitude, the distance between the target spacecraft and the origin of the Earth, or center of the Earth. Then we have LZ unit vector being the same as the orbit angular momentum vector H divided by its norm, because again, LZ is another unit vector that comprises, which is comprised within LVLH. And as per usual, the y direction is obtained by the cross product of LZ with LX, like that. So this is the mathematical definition of LVLH, local, vertical, local, horizontal reference frame. And that was exactly the same for the orbital reference frame, which I'm going to report here in red, just so that you can remember. We had OX from the center of the Earth, from M1, essentially pointing at the target spacecraft, so that was our OX. Our OZ was coinciding with the orbit angular momentum vector H, OZ, and then OY, also in the same plane as OX, was obtained by the cross product of these two. And as the spacecraft was rotating around the planet, then OX would also rotate to always point at the target spacecraft or at the spacecraft itself. Whereas here, the only difference is that the origin is moved directly onto the target itself, but you can see that the vectors would still need to rotate to maintain the alignment between LX and RT vector at all times, okay? But sometime in the future, you will get RT vector here because target spacecraft would have moved from here to over there, and therefore then LX would be here, LY would have been shifted there, and LZ would still maintain its direction because the time derivative of the orbit angular momentum vector is being considered to be 0 whenever we neglect orbital perturbations, which is what we're going to do in this chapter. Okay, we don't want to overcomplexify things by throwing orbital perturbations on top of another spacecraft orbiting around, and that would get just too messy. So what we're going to consider is one chaser spacecraft, one target spacecraft, and the primary body. Okay? So this is LVLH reference frame. Nothing too difficult here, given the fact that we had already used the orbital reference frame extensively in Chapter 3. The only difference, again, is the origin of the reference frame. Now, I shouldn't have erased that. So, M1, target spacecraft with RT position vector, target chaser spacecraft somewhere else. We're going to define its position vector with respect to M1 as being RC vector, C for chaser, T for target. And you have the solar panels, as per usual. Okay, so we have those two spacecraft orbiting around their own orbit with respect to M1. And then what we're going to do is to define a new vector, which is the position vector of the chaser spacecraft with respect to the target spacecraft, and that one is going to be denoted by rho. Okay? So, ultimately in this section, nonlinear relative equations of motion will be to derive the acceleration of the chaser spacecraft with respect to the target spacecraft. Or in other words, to come up with an expression for R vector double dot, like that. But the starting point is to look at the position only. Okay? So position of chaser with respect to the target being rho vector. And then what we can do is to define rho vector in terms of its components in our new reference frame we've just defined, which is LVLH, denoted by capital calligraphic F subscript L, LVLH, in terms of the components of this vector inside that specific reference frame. Don't forget the underline notation. And then we'll just arbitrarily define the components x, y, z of this vector seen in LVLH as being x, y, z scalar components. And of course the transpose. Okay? So that is how we can express this vector in terms of its components in LVLH. Now that we know that, we can also go back here and look at the position vector itself and how to obtain it from those two position vectors from either spacecraft all the way to the primary body. And then we're going to say that rho plus RT, or RT plus rho, doesn't matter, is going to be equal to our chaser spacecraft position vector, like that. Or in other words, that rho vector, the position of spacecraft, of the chaser spacecraft with respect to the target spacecraft, is simply going to be equal to RC minus RT, like that. Okay, same thing. Now what we know from kinematics equations that we've derived in chapter 1 is that if you were to look at RC, just copying down that equation here for convenience, RT plus rho, we know how to obtain the inertial derivative of this vector. Do we? Yes. So this is position level equation. Now the velocity equation is going to be RC inertial derivative. And here I'm just applying the transport theorem. Yes, it's coming back at us. So that's our RC vector hollow plus angular velocity vector between LVLH reference frame that has its origin at the target spacecraft with respect to ECI, cross product RC vector, like that. We also know, also from kinematics, that the acceleration level inertial equation like that is going to be RC double hollow plus the angular velocity between the moving reference frame, which is LVLH, and the inertial one, ECI. This inertial derivative, cross product position of our chaser spacecraft with respect to the origin of ECI, plus 2 times omega Li vector cross product RC vector hollow plus omega Li cross product omega Li cross product RC vector. Remember, that was our kinematic acceleration equation that we've derived at the very end of chapter 1. This is our Coriolis / centripetal acceleration equation. And that was the velocity equation straight from the transport theorem that tells us that the inertial derivative of vector is equal to the non-inertial derivative of the same vector plus the angular rate between the non-inertial reference frame, LVLH in that case, and the inertial one, cross product of the position vector itself. Okay? So this is straight from transport theorem. And this one is from let's call it Coriolis acceleration kinematics equation. and that position equation was just from head to tail sum of two vectors. Well, how is that helping us? Those are a vectorial equation, and we said that the ultimate objective was to get rho double dot vector, but specifically, and I didn't tell you that, but what we wanted out of it was the x, y, z components of this acceleration vector. This is our ultimate goal here. So what we're going to do next, because those equations include inertial derivative, non-inertial derivative, this is an indication that taking their components in the appropriate reference frame would be the next step, okay? And we had done that in a previous chapter. We had looked at the components of a non-inertial derivative and the components of an inertial derivative. And again, the only difference is in which reference frame we are looking at those two things. All right, so let's do it. So what we're going to do now is look at all the vectors involved in those three equations and write them up in terms of their components in LVLH. Okay? So we had RC vector, and we're going to write in LVLH. RC vector components in LVLH like that. So to determine this, we need to go back to RT plus rho equal to RC that we had previously on the board, and such that RC was equal to RT vector plus rho, and then look at those two things in LVLH. So in LVLH RT, this is Lx, Ly, and Lz out of the board. RT vector only has one non-zero component, which is all about the component along the Lx unit direction, because as the target spacecraft moves along its orbit, then Lx unit vector will always track the position of the spacecraft, and therefore Lx will always be collinear with RT, such that the components of RT in LVLH will simply be RT magnitude 0, 0. And previously I had just defined this in terms of components in LVLH to be vectrix LVLH transpose and simply X, Y, Z. Okay? Such that here the position of the chaser spacecraft seen in LVLH will become RT plus X along Lx unit direction, Y along the Ly unit direction, and Z along the Lz unit direction. Such that our RC vector hollow is going to be the derivative of RC vector, but seen in the moving reference frame. There's no choice here because of the hollow operator, which tells us or specifies to us that the derivative has to be in LVLH. So let's do it. This in LVLH. And then for the components, I just use the standard time derivative operator like this and like that. Okay? If you remember the acceleration level kinematics equation for RC, we also had RC double hollow. Well, it turns out that this is just going to be LT, the vectrix LVLH transpose, and then RT double dot plus X double dot, Y double dot, and Z double dot, like this. Okay? Next, we have the angular velocity vector between the moving reference frame and the non-moving one. This is omega Li, expressed in LVLH, is going to have two zero components along x and y, and the non-zero component is going to be along Lz only because LVLH spins about the Iz direction, or about the Lz direction, okay? Like this, so 0 in the direction of Lx, 0 along the direction of Ly, but theta dot, the rate of change in true anomaly, about Lz unit direction, such that omega Li dot that we had in the equation expressed in LVLH is just going to be 0, 0, theta, double dot, like that. Okay. Now with all these pieces being defined in terms of their components in LVLH, we can go back to the acceleration equation and plug each of these pieces into that equation. All right. So we had, I'm going to need a bit more space, so let me erase everything. So that was our RC vector double derivative in terms of inertial derivative was equal to, now everything on the right hand side is going to be written in terms of components in LVLH. So instead of copying the LVLH vectorics all over the place every time I hit a vector, I'm going to factor it out right up front like that, and just do the vectorial operations that we had, but in terms of components directly, because by now I am familiar with the content in chapter 1, right? So I know how to turn vector operations into vector component operations with the skew symmetric matrices, the dot product turning into components, transpose times components, and all, yada, yada, yada. So we had first the R vector double hollow. So in terms of components, as we just determined, it's going to be RT double dot, X double dot, Y double dot, and Z double dot. Plus we had omega dot, which is this, and theta double dot. Right, because omega is the angular rate, and that is the rate of change in an angle, such that omega dot is the second derivative of the angle variation. Now this vector was being cross product with RC. A cross product in terms of components turns into a skew symmetric matrix. So I'm going to have to build a 3 by 3 out of that 3 by 1, as we said in chapter 1, times RC, which was RT plus X, Y, and Z, plus 2. And in terms of vectors, we had omega cross product, omega 0, 0, theta dot. Cross product turns into skew symmetric matrix, times RC dot, which is RT dot plus X dot, Y dot, and Z dot, plus, now we had the omega cross R. So our omega is 0, 0, theta dot. Cross product becomes skew symmetric of omega, and then cross product becomes skew symmetric again of RC, which is RT plus X, Y, and Z. And then you close a curly bracket. So all I did was to look at each individual vector that was part of my initial acceleration equations based on kinematics, and yeah, turn all vectors in terms of the components in LVLH, right? I didn't have to think too much. So that's what we end up with. I'm going to let you figure out the details. So how to construct the 3x3 out of that, 3x3 out of that, multiply both together, multiply the result with this, and then carry out the linear algebraic operations. But here I'm going to give you the results, and hopefully you're able by now to obtain the same result. Otherwise, as a heads up, you might have a hard time in the exam. Okay? So RT double dot plus X double dot minus theta double dot times Y minus 2 theta dot Y dot minus theta dot square RT plus X. So all this is for the X components of the chaser spacecraft acceleration vector in terms of components in LVLH. All right. For the Y components, we have Y double dot plus theta double dot times RT plus X plus 2 theta dot RT dot plus X dot and minus theta dot square times Y. Okay, the square terms in terms of theta dot comes from the multiplication of this 3x3 with this 3x3 and that one. Okay, so we had theta dot square times RT plus X, the X component, whereas here we have theta dot square times Y, and you'll see that the last one is going to be 0 because the position of those zeros in the 3x3 matrices multiplied together turns out to be 0. So there's no Z component here, and in fact, because of those matrices that are being turned into skew-symmetric matrices, and the 0 multiplies this and that, all we have for the Z component is Z double dot like that. Okay? What we're going to do next is keep playing with that equation till we get a nice result out of it. And specifically, we will find alternate expressions for theta double dot and RT double dot, because those aren't very convenient for us in order to linearize them at the end of the day to then gain a better understanding of the relative motion between two spacecraft on orbit. So I'm going to say where theta double dot, well, not yet. Let's first begin with theta dot and get theta double dot because we don't know yet what it is equal to. But if you remember, I believe in chapter 2, might have been chapter 3, we had obtained orbit specific angular momentum H equal to R square theta dot. Well, because here the variables are associated with the target spacecraft in terms of true anomaly, rate, true anomaly acceleration, and RT. This is going to be the specific orbital angular momentum of our target spacecraft. Okay, because again, those two variables are for the target spacecraft. And if we were to take the time derivative of H, we are going to get 2 times RT times RT dot theta dot plus RT square theta double dot, and say that this has to be equal to 0 if we are neglecting any perturbations affecting the motion of either spacecraft on orbit, which is the approach taken here. So I said I want to replace theta double dot with something else. Well, all I have to do now is to solve that expression for theta double dot, which is going to give me theta double dot equal minus 2 RT dot theta dot over RT. Okay, let's keep that in our back pocket. So I'm going to rewrite it over there. 2 RT dot theta dot over RT. That wasn't too bad. Now, also what we want is to get an expression for RT double dot. So I'm going to begin with RT in terms of, what the hell is that? RT in terms of vector expressed in LVLH, in terms of components of this vector in LVLH. And because RT always follows Lx, as we did previously, means that we're going to get RT magnitude 0, 0, all along Lx direction. Now, if you were to take the time derivative of this, the initial time derivative of this vector twice, to do that, you need to consider the initial time derivative of this vectrix and involve the angular velocity between LVLH and ECI, and ultimately end up with an expression that is going to be equal to vectrix L transpose, and then here we would see RT double dot minus theta dot, which is your omega Li square times RT vector, and obviously 0, 0, because everything happens over Lx for the target spacecraft. Next, what we can do is to use the two-body equation of motion to also write RT double dot, right? That's one way to obtain it, but we also know that RT double dot vector can also be equal to minus mu over RT vector over RT norm cube. I can turn this side in terms of components by writing vectrix L transpose of minus mu. This vector in terms of components turns into RT and LVLH. And all this over RT cube, or in other words, vectrix L transpose times a scalar times a 3×1 that contains the x, y, z components of the target spacecraft position vector with respect to M1 seen in LVLH, and that is just RT 0, 0, like this. I need almost all equations here. So let me just write that RT acceleration vector equal to vectors RT double dot minus theta dot square RT position 0, 0. Okay? So that I can erase all of this. So glad I ordered such a big whiteboard to play with. It weighs a ton. Was pretty expensive, but then in the end I have a lot of room to play with equations, okay? And all this was for RT inertial acceleration too, okay? So RT, I can just rewrite it by putting the minus sign in front of everything. So minus vectrix LVLH transpose times mu over RT square. That's for the x component, and 0, 0 the y and z components. Now this is one expression for RT acceleration vector. This is another one. So obviously they both need to be equal to each other. So I'm going to say RT inertial acceleration equal to RT inertial acceleration, and thereby say that minus mu over RT square RT square 0, 0. This term has to be equal to this term. Into RT double dot minus theta dot square RT 0, 0. Like this, I'm just equating the components of both vectors because both vectors happen to be the same one. Okay? Or in other words, if I just look at the z component on either side of that equation, I can then just solve that equation for RT double dot, which is going to be equal to theta dot square RT minus mu over RT square, like that. Okay? And what was the objective of doing this? Well, the objective was to have an expression, an alternate expression for RT double dot and another expression for theta double dot. So I have theta double dot is equal to this from before, and now I'm going to use this expression back into here. Oh no. Well, whatever that was. I saved it for so long just in the end to cancel it out. Oh well. Well, turns out that if you plug what we had here in this expression and that one for RT double dot, we would end up with RC inertial acceleration equal to this, and then times the components of this vector in LVLH. Okay, where the x component is going to be x acceleration minus theta dot square x minus 2 theta dot y dot minus y that multiplies RT dot over RT, and all this minus mu over RT square. All this is for the x component of this vector. So the acceleration of the chaser spacecraft with respect to the center of the Earth, expressed in terms of the angular velocity of the LVLH reference frame. This is your theta dot. And in terms of the relative motion between the chaser spacecraft with respect to the target spacecraft. So those are the x, y, z components in terms of position, velocities, and acceleration. So y double dot minus theta dot square times y plus 2 theta dot times x dot minus x times RT dot over RT. That's it for the y component. And then the z component of RC acceleration in LVLH is going to be, well, same as before, z double dot. Okay? But I said that the ultimate objective was to get expressions for this, that, and that. the x, y, z components of the acceleration of the chaser spacecraft with respect to the target spacecraft. So I have 1/2 of it, but then I would need to equate that to RC double dot using another expression for RC double dot. And turns out that we have our good old two-body equations of motion that does just this, and we'll get rid of all the vectors everywhere and just end up with a bunch of scalars, okay? So I'm going to write for RC double dot on this side in terms of components in LVLH, that this is vectrix LVLH, and then minus mu times RC norm cube times components of RC in LVLH. Okay, this is for this vector equal to all of this. And because we know the components of RC vector in LVLH, we could just rewrite this as being transpose vectrix LVLH, or minus, if you will, times mu over RC cube that multiplies RT plus X, Y, and Z. Okay? All this equal to vectrix LVLH times this. Or I'm just going to report this result on top here, make my life easier. And say that this is minus this times RT plus X, Y, and Z. So this, where did the mu go? I had the mu over R cubed, right? I forgot it. Make some room here. Minus vectrix LVLH transpose of mu over RC cubed that multiplies this 3 by 1. Such that in the end, my three equations of motion for the chaser's acceleration with respect to the target spacecraft in terms of components and LVLH are going to be, well, I'm just rewriting this, so x double dot minus theta dot square x minus 2 theta dot multiplies y dot minus y RT dot over RT minus mu over RT square, and all this equal to minus mu over RC cube times RT plus X. Okay, so I've done this. So essentially I just took the vectrix LVLH away from both sides of that equation. I only kept the scalar parts. And then I'm going to write y double dot minus theta dot y plus 2 theta dot that multiplies x dot minus x RT dot over RT equal to minus mu over RC cube times y. Let me just double check, make sure I didn't do a silly mistake somewhere. That looks about right. And hopefully I didn't screw up the z equation, because z is really simple. That is just that z double dot is equal to minus mu over RC cube times z. Wow. Aren't those equations beautiful? Yes, and that's why I like formation flying quite a bit, because the equations are so elegant, okay? So if what you want to know is how is this chaser spacecraft accelerate away or towards target spacecraft, T target, C chaser, relative position, and then time derivative, relative velocity, and ultimately relative acceleration, and LV LH equal to X double dot, Y double dot, double dot, right? This is what we're looking at. How does this chaser spacecraft accelerate away towards the target spacecraft? All you have to do is solve those three equations for these three quantities, and boom, you get your answer. However, to do that, we would need a numerical simulator that would perform the integration numerically. Because based on those equations of motion, right, we're talking acceleration, so obviously this is equations of motion. In that case, relative motion, because x, y, z quantify the relative motion between chaser and target. Well, for those equations, there is no analytical solution that can be derived. Or in other words, we cannot go directly to this expression and find xt, yt, and zt equal to blah, 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 blah. And that is because those equations are highly non-linear, as predicted by the title of this subsection. So the bulk of the remaining work in that section is to figure a way to simplify these equations down to a simpler nonlinear equation of motion model. So we'll still be talking about nonlinear dynamics, but simpler, such that that simpler nonlinear equation of relative motion will be linearized eventually. And then once we would have obtained the linear equations of relative motion, we will be able to express x, y, z components of the relative position vector as function of time, okay, and get explicit solutions for the relative motion. So let's keep working on those nonlinear equations of motion, and specifically, if we assume, so those equations are exact, okay? There were no underlying assumptions behind this derivation other than that there's no orbital perturbations. So I'm going to refer to those as exact equations of relative motion. From there on, the equations we're going to derive won't be exact anymore because we're going to make several assumptions along the way, okay? But ultimately, the objective is, again, to make those assumptions to end up with some linear set of differential equations for which we know how to derive the explicit time-based solution. Okay, so first assumption here is that we're going to assume that x, y, z components of this relative position vector between chaser and target is going to be much smaller than the distance between the target and M1, okay? So essentially we're considering that both spacecraft, chaser and target, are operating in close proximity, okay? So if both spacecraft are close enough such that the norm of this is much smaller than the norm of this RT vector, then the follow-up equations will be valid, okay? So again, x, y, z, much smaller than RT in terms of magnitude of this position vector for the target spacecraft, okay? Doing so allow us to write that RC, which technically speaking is the Euclidean norm of RC components in LVLH, which is equivalent to saying the square root of RC components in LVLH, which is RT plus X square plus Y square plus z squared, if you remember, okay? Which means that this RC magnitude is going to be equal to RT squared plus 2RTX plus x squared plus y squared plus z squared. Okay, this is how we could calculate the norm of RC vector given its components. And just to play a little bit more with that equation, I'm going to factor out my RT squared, square root of, so my RT times square root of 1 plus 2x over RT. Hopefully you can all see that on the screen. Plus x squared plus y squared plus z squared, and all this divided by RT squared. Now, do you remember the assumption I've just discussed about? The fact that we're assuming that the distance between chaser and target spacecraft was small compared to the distance between the Earth and the target spacecraft, such that x, y, z components were much smaller than RT norm. It means that based on this, I can approximate my RC to be approximately equal to RT times square root of 1 plus something small over something large. I'm going to leave it as is, but then something small to the square over something large being squared as well. This I'm going to say, no, that this is too much. I'm going to consider that this term is 0. Okay? So RC is then becoming approximately equal to RT square root of 1 plus 2x over RT. Under the assumption that x, y, z components are much smaller than RT. Okay? I mean, you don't want to go as far as saying that this is also equal to 0, because that would mean that you are not approximating that RC is exactly equal to RT, and that just doesn't make sense. In that case, you're nullifying the relative position between both spacecraft. Okay? That's just going one step too much into the process of assumptions here. So that's what we have. But if you look at the equations we had in blue, the exact set of nonlinear equations, our RC happens to be used in terms of 1 over RC cubed. Okay? So with that in mind, I'm going to say that my RC to the -3 or 1 over RC cubed, which is what I'm going to have to play with in those equations above. It's going to be approximated to RT to the power -3 times 1 plus 2x over RT to the power -3 over 2. Well, that's not very helpful. It looks quite a bit complex now. And I said I want to simplify things. Well, let's see what we can do with that expression. Turns out there is the binomial expansion theorem. That says that if you have a plus b and all this to the power n, this is actually equal to a to the n plus n times a to the n minus 1 times b plus n times n minus 1 over 2 whatever this is called. I have a blank here, exclamation mark. But it doesn't matter in the end because we'll end up using it. So times n minus 2 of b squared. And then the expansion just keeps going on and going on. So it depends on which degree of fidelity you'd like to approximate this term. So if you want to have something very accurate, you're going to use the full expansion. But for all practical purposes, we'll just limit ourselves to the first two terms of this almost infinite series and approximate that here to be equal to something that looks like that, okay? So, meaning that my RC 1 over RC cube is going to be approximately equal to RT 1 over RT cubed, so minus 3. And I'm going to use the binomial expansion theorem applied to this situation here, where my exponent n is minus 3 over 2, where my a is 1, and where my b is 2x over RT, to write that this is then being multiplied with so this is 1 to the power minus 3 over 2, so just 1. And then b is this, so plus n, which is minus 3 over 2, times a, which is 1, whatever power is just 1, times b, which is 2x over RT, or in other words, 1 minus 3x over RT, because the 2 cancel out. So this is how I could replace my 1 over RC cubed in my original nonlinear exact equations of relative motion. But still, that's not very helpful, right? So what we're going to do is keep playing with the equations until we find something helpful out of this. So done with the binomial expansion theorem. I'm going to keep that result. Which means that when I had all those three terms on the right-hand side of those three equations collected in a matrix form, we had minus mu RC cubed times RT plus X, Y, and Z. Okay, so this is the acceleration of our chaser spacecraft in terms of components, LVLH like that. This is going to be turned into something that makes use of this term. So minus mu over 1 over RC cubed, so RT cubed times 1 minus 3x over RT, and all this times the 3 by 1 matrix, which is RT plus X, Y, and Z. Okay? So I'm just looking at the specific terms I have on the right-hand side of those three equations and see how I could rewrite that based on the assumption we made, and that was that X, Y, Z was much smaller than RT magnitude. So those terms here could be replaced by this. This isn't clean enough for me, so I'm just going to clean that up a little bit and saying that this could be equal to minus mu over RT cubed. Well, actually, I'm going to leave it as it is for now. So I'm going to pull everything in the 3 by 1 matrix and just write 1 minus 3x over RT. This times RT plus X, 1 minus 3x over RT, that multiplies Y, and finally 1 minus 3x over RT, that multiplies Z. know what? I think I'm gonna get rid of those equations because they're way too big and they eat up most of the space I need to derive equations, and that gets very annoying. So I'm going to refer to those equations as the exact nonlinear equations of motion, i.e. the blue equations that were on the board, okay? Just keep in mind that that's the equations I will be referring to in the near future. So I can have some room. So minus mu RC cubed and RT plus X, Y, Z. I'm going to say that this is replaced by minus mu over RT cubed instead. Times RT plus X and then minus 3x RT over RT, and then minus 3x squared over RT. That makes sense? RT plus X minus 3 times X over X, and then minus 3x squared over RT. Yeah, this is my X component. For the Y component, it's going to be Y minus 3x Y over RT. And finally for Z, it is going to be the same as Y, but just with Z. So Z minus 3x Z over RT, just like that. Okay, now we have to remember what we are doing here. We are deriving equations, but for what purpose? So let me step back a little bit to make sure that we're all on the same page. So the idea was to go from the blue equations, the exact nonlinear equations of relative motion that describes the motion between chaser spacecraft and the target spacecraft. Those were exact, the best we could get, okay? Assuming there's no perturbations, obviously. But the problem with those is that there's no analytical solution that would provide us an equation for X as function of time, Y function of time, and Z function of time. So we said, okay, what we're going to do is to then linearize those nonlinear linear equations of motion, and the process to obtain a linear set of differential equations is to make some assumptions. The first one of which was to assume that X, Y, Z components were small compared to RT magnitude. And by doing so, I said that we're going to end up somewhere else with new equations of motion that would still be nonlinear. So we're going to make assumptions like that one after the other until the nonlinear equations of motion become linear at the end of the day. And then we'll be able to come up with the explicit solution for X, Y, Z function of time. So this is just the first step in terms of simplifying the blue equations we had on the board. And because we are under the assumption that X, Y, Z are small compared to RT, what I'm going to do here is to neglect second order terms, okay? So when I have X, which is small, that multiplies Y, which is also small, it's as if I'm taking the square of a small quantity divided by a big quantity, and I'm going to say that this is approximately equal to 0. Same here, X times Z, so two small numbers being multiplied together gives me something even smaller, divided by something big, RT, so that is equal to 0. I have a square term of something small over something large, that is 0. This is RT over RT, so I'm going to be left with minus mu over RC cubed of RT plus X, Y, and Z equal to minus mu RT cubed now of RT X minus 3X, so that is minus 2X, and then Y and Z. That is a lot nicer than what we had previously in terms of the intermediate results. to go from the right-hand sides of the blue equations to something else. That something else being derived due to the fact that the relative distance between both spacecraft is considered small compared to the distance between target and M1. Okay. Making use of this fact. So if I were to substitute the right-hand sides of my three equations I had in blue with those three equations, so this is one equation, this is another one, and the last one is z times this, I will end up with another set of equations of motion, which will be equal to x double dot minus x theta dot plus 2 mu over r t cube minus 2 theta dot y dot minus theta double dot y, all this equal to 0. Y double dot minus y multiplies theta dot, this is square, theta dot square minus mu over RT cube plus 2 theta dot x dot plus x plus theta double dot x equal to 0. And finally, the z equation, which is always the simplest equation among all three, is going to be z double dot plus mu over RT cube times z. Okay, the x is here, the y is there. Okay. And all this equal to 0. So what we have here is some other equations of motion that are still nonlinear. Nonlinear equations of relative motion. The thing here is that they aren't exact anymore. The blue ones we had were exact. And they're not exact because they work only under the assumption that x, y, z are small compared to RT magnitude. So whenever that is the case, so whenever you have two spacecraft operating in close proximity, you could roll back to those equations. Instead of using the exact ones, you could use those ones. Although, to be honest, there's no real benefits to do so. You might as well just use the exact ones because, again, those won't even provide you with an explicit solution for x, y, z as function of time equal to something because they are still nonlinear. So this is just, see it as an intermediary step towards the derivation of the fully linear set of equations of motion, from which we'll then be able to obtain x, y, z as function of time. And this, ladies and gentlemen, is going to be left to another lecture. So there's only one step left to go from nonlinear equations of motion down to linear equations of motion, from which we'll obtain the time-explicit solution for x, y, z. And based on that, we're going to talk about practical implications, making use of those equations. All right, but that'll be next time. Hope you still enjoyed the lectures, and I'll see you soon. Bye.